Just let's give a few minutes or a few seconds for the people to join, for the registrants to join. The number of attendees is increasing. Anyway, I guess we can start now. We already have a very dense subject today to cover. So good morning, good afternoon, good evening, wherever you are. We are pleased to have you with us today in our soil improvement webinar. Rigid inclusion, PVDs, consolidation, soil improvement, all are keywords for geotechnical engineers, and usually they wonder about it. Stay tuned for more info about these keywords. Let me introduce our presenters today. Today, we will have with us our usual webinar rockstar, Richard Vitas. Hello, Richard.
Yeah, good morning, good afternoon, everyone.
And we will have also Jérôme Racinier. What can we say about Jérôme? Jérôme is a reference in soil improvement. He also is a past vice president of TC 211 in ground improvement in ISMGE and the engineering director of Menar Group. Hello, Jérôme.
Hello, Daniel. Hello, everyone.
Jérôme and Richard, we are happy to have you with us today. Now, let's start. And to understand better you and what are the challenges that you are facing, please answer the following questions, of course, in soil improvement. Okay, so the first poll is there. We'll give a few more seconds for the attendees to continue answering. Okay, let's stop. So rigid inclusion is the most popular one. And the another question, please also answer it. This is about the challenges that you are facing in your soil improvement modeling. And I think this is a very important question. Oh. The attendees are still, their number is still increasing. So we will give a few more seconds for the people to answer. Okay, let's close. Let's share the results so you can see. And also here, the biggest challenge for the audience is analyzing the behavior of rigid inclusion under complex
Loading, I think.
Loading, yeah.
Loading, yes.
You're muted, Daniel.
Okay, now is it good?
Okay, Daniel.
Great. Now, we will speak about the series of the soil improvement with PLAXIS. The first one will be the webinar that we are watching, and we had 3 previous blogs that were also very interesting. You can check them when you want by going to the soil improvement page. Also, by registering to this webinar, you will receive some practical examples of PLAXIS on soil improvement, where you will find practical examples on PVDs, stone columns, and rigid inclusion. But don't worry, if you are interested also in other topics, Richard got you covered. He also prepared another practical examples on tunnels, pile foundation, and many other foundation problems. Okay, so and what a better way to learn more than by applying what you learned today, what you read in the blogs, and what you saw in the practical examples. Just fill the free trial request in our campaign page, in the soil improvement campaign page, and you will be able to try them all and learn more. Now, what's today on the table? What we will discuss? We will discuss the key modeling techniques for soil improvement with PLAXIS, and a case study for PVDs, and another case study with footing over soil reinforced by rigid inclusion subjected to complex loading. For your questions, please place it in the place shown on the screen. And as we care about your feedback, and especially for that subject for future webinars, please fill the feedback that we will receive and tell us how we did today and what would be important for you to cover in the future webinars. Okay, now I think that we will start. Richard, the stage is yours.
Thank you. I just need for me to be able to share my screen. So I think I'd like to be made a presenter. There we go. So just
yeah.
Okay. Thank you very much, Daniel. Thank you very much, Jerome, for organizing this presentation today and for joining us, Jerome, and share your very valuable experience. So I will be providing the first elements of this webinar by focusing a bit on not much on the practical aspect, but maybe more on the theoretical aspect from a PLAXIS usage point of view regarding soil improvement modeling with PLAXIS. So just to start with, well, I get a few introduction. Well, I guess you are all familiar, I guess, in this room, that soil improvement techniques and what the main purpose of soil improvement techniques are. It is to fundamentally improve to modify and improve the physical properties of the soil in order to ultimately improve its loading bearing capacity, reduce settlement, and also in some cases where it's relevant, mitigate the risk of liquefaction. These are fundamentally. So there is these different techniques to do that, and it might be interesting to be able to efficiently model them in PLAXIS to optimize your design. So when it comes to application of numerical modeling for soil improvement techniques, well, depending on the different type of methods that would require different modeling techniques. So we can briefly start talking about compaction methods. So we have the first one of them I like to talk about are dynamic methods, maybe not the most popular one, but still used to quite some extent, like dynamic compaction and compaction blasting, especially dynamic compaction. Well, those are not commonly practiced in finite element modeling, I would say, due to their complexity, especially of accurately modeling the dynamic impact and transient behavior. So it's still possible. There are some possibilities to do that, but this is not an exercise which is commonly undertaken, I would say. However, compaction methods that are relying on static methods like preloading, often combined with vertical drains, as we will be showing today, are quite common. So the key points here consist of applying a static load, and property of which will be enhanced over time by consolidation. And this is suitable for cohesive soil like soft clays. So this would require usually doing consolidation analysis, which are coupled analysis in PLAXIS, and it seems to be a key aspect. And also, as I will be mentioning a bit later, permeability adjustments might be necessary depending on the model used. I will explain you why. So this is what I will be first focusing today in my presentation, and the use of PLAXIS for the modeling of preloading with prefabricated vertical drains. Then there are other types of techniques that could also be used in PLAXIS, talking about like all soil improvement techniques which do not induce displacement of the soil. I could talk about soil freezing. I could talk about injections. Well, for soil freezing, usually these are also quite complex methods that requires specific constitutive models to accurately the behavior of the frozen soil, and especially the change from normal soil to frozen soil. Here as well, those type of analyses are quite seldom and not commonly being performed. I mean, we do have some papers, but this is very very limited type of analysis. On the other hand, injections are performed, and well, usually what people are doing in that case, they are just replacing the property of the soil with the one of improved soil after the injection process has taken place, by just like wishing in place a new material correspond to the improved soil material. This is something that I've seen quite a certain number of times. I will not be talking about today, but this is a possibility with respect to that particular type of soil improvement techniques. And then the last one, the one related to improving by adding structural elements with or without soil displacement. And especially here, we'll be referring to rigid inclusion and foam columns, which are the two most common type of soil improvement techniques that I will also be briefly talking about in the second part of my presentation, before I then give the floor to Jérôme. So, modeling prefabricated vertical drains in PLAXIS, PVDs. So, well, the key steps, the key modeling steps with that respect. First, defining the geometry by considering specifically the PVD layout within your PLAXIS model, and especially with the proper consideration of drain spacing, depth, and arrangement. Well, usually in 2D at least, that's relatively easy and straightforward. Then the second part is focusing on the material properties. This is where I will be spending most of the time during this presentation, this first part of this presentation, where we will need to assign appropriate properties to the constituted materials, and especially the definition of permeability or equivalent permeability, at least as I will explain it later. Then the third step would be to define the boundary conditions and the analysis setup by properly applying also the initial conditions, the drainage boundaries, and finally define the relevant different construction stages. And then finally, result interpretation in terms of evaluating settlements, pore pressure distributions, and effectiveness, analyzing the effectiveness of PVDs by either checking the factor of safety at different times, as well as the evolution of the degree of consolidation. So, as I was explaining you, one of the key aspects in defining the properties is to define the permeability of the material. So, if we look at I would say the disposition, the setup of the drain, I'm looking at it from the top plane here. If I compare on the left-hand side the way those PVDs are being placed, and the way we will be modeling it, or modeling them, I would say, in a 2D framework, well, we see that in the 2D plane strain model, we are introducing like a drainage lens that is uniform and cannot properly render this spatial disposition in 3D, where you could see that depending on the location where you are in the soil, you are introducing different drainage length. So in fact, I would say if you would use in 2D the same permeability, considering that in 2D the drainage lengths are shorter, you will speed up the consolidation process. So one way to address that is to, that's not the only one, but it's one of them, is to introduce the concept of equivalent permeability, which consists of reducing the permeability in order to match the proper degree of consolidation in 2D plane strains and the one you would have observed in 3D. That's one of them. And for that, there exists papers and methods that provide equivalent permeability. The three most popular are the one from Hurd, Indra, Ratna, and Shep. So this will be not described in this presentation, but in the paper and the example that we will be providing, we will provide extensive reference and explanation on what those methods exactly consist of. And then the strategy is to first start using those probabilities value, and then set up these two models. So on the left-hand side, a reference axis symmetrical model, the radius of which is defined such that the drain affects a certain the proper area relevant with respect to the drain spacing. So usually, if you are assuming that the drain spacing are placed over a perfect rectangular pattern, you could say that this would be the influence area would be S to the power 2, basically S times S. So you are making sure that your axis symmetrical model area is equal to S to the power 2, and you are just defining the drain in the middle, and you start applying a load and look at the evolution of the degree of consolidation with time using the proper permeability values. And next to that model, you are defining the equivalent unit cell model, but in 2D plane strain, using usually the same as a model with the drain spacing. And you are making sure that while loading that 2D plane strain model with the same load as the 2D axis symmetrical model, you are obtaining the exact same evolution of the degree of consolidation with time. That's the idea. And usually you start from this formula I provided before, and then you can fine-tune them by slightly playing with the permeabilities value until you are obtaining a perfect matching. And this is one of the methods. I have heard some people using different methods. Maybe Jérôme could elaborate a bit more on those, but some people prefer not to change the permeability, but start playing with the spacing between the drains, which at the end of the day, well, enables you to obtain also the same type of results with the same type, with the correct evolution of the degree of consolidation for a plane strain situation. So this is an example here of what this degree of consolidation would look like. And of course, you can do that with or without the consideration of the smear zone, you know, that zone that is affected by the drain installation process, eventually. So yeah, this is for the techniques. And as I was explaining you, if you want to have all the details on how such models could be set up, we have been publishing on our practical example wiki page a complete explanations of this modeling process along with the corresponding PLAXIS models in 2D. So if you are interested, feel free to take a look at them. And then finally, when this has been done, well, you can set up the complete 2D model like this way. So what you see here in that particular case, the blue vertical lines corresponds to the drain position, while in PLAXIS, they are nothing more than just applying additional groundwater flow boundary condition over which you are enforcing the water head to remain at a certain location that you fix. That's the way the drain elements are being implemented in PLAXIS. It is simply a boundary conditions for the flow problem. You do also observe that in between the drains, we are using different characteristics due to the fact that that in those areas we are using different permeabilities value for matching the proper degree of consolidation, as I was explaining before. The remaining soil remains unchanged. We do see here the location of the water table. We are enforcing here close, so water influx to be equal to 0 due to the fact that we are considering here a plane of symmetry. And then finally, we are building up the embankment in stages, and we are monitoring as a function of time the settlement, the evolution of the degree of consolidation or the excess pore water pressure in between the drains, as well as for each construction stages, the corresponding factor of safety and associated failure mechanism to check whether they are above acceptable values. That's, in a nutshell, the process of running this type of analysis in PLAXIS. This brings me to the second part of my presentation, now more focusing on column-based soil improvement modeling techniques, fundamentally stone columns and rigid inclusions. So in that situation, well, we are interested in still performing those analysis in 2D, which also requires us to do always some calibration processes. As I will explain you, the 2D plane strength condition does not enable you to properly consider the stress redistribution within the soil, and especially arching effects, which could be, for instance, taking place in the mattress if you talk about rigid inclusion, or stone columns as well as eventually the proper probability, because if you start talking about stone columns, you will also introduce along the stone columns drainage path, basically. So the stone columns will considerably affect and reduce the drainage length. And that's because in 2D, a stone column is nothing more than a kind of continuous wall. And if you compare that continuous wall to what the stone columns looks like in reality, you will clearly understand that if you are representing the stone columns, which is here, like this in PLAXIS 2D model, yeah, you might be considering also playing with the permeabilities between the stone columns to perfectly match the proper degree of consolidation. Well, honestly speaking, from my experience in this type of problem, if you don't, I don't think it will affect that much, that significantly the evolution of the degree of consolidation. But theoretically speaking, you may argue that you maybe should. So in terms of rigid inclusion, talking about the fact that we are doing a 2D model in 2D plane strain to represent a phenomena which are fundamentally 3D, we need to be playing around. I will explain that later. So the rigid inclusion now themselves in 2D will be introduced by means of embedded beam elements. So those are beam elements which are connected to the surrounding soil using node-to-node coupling springs, basically, to which the user specify the skin resistance, lateral resistance eventually, as well as tip resistance. And also, and just define them this way. So we will explain later on how you can also calibrate those embedded beam elements such that they do reproduce properly the behavior of a rigid inclusion. The next type of problem are related to stone columns. So in that case, well, you could have, in terms of making a 2D equivalent model, two strategy to get equivalence. Either you are playing with the wall thickness and representing the stone columns, which is usually what I'm doing most of the time. But you could also stick and define the wall thickness to be equal to the diameter of the stone columns and play with the stiffness of the material inside the stone columns, also to get comparable results with the 3D situation. So in both approaches, anyway, you understand that there is a need to set up on beforehand unit cell models and do this calibration process, which is what I'm explaining right now. So this is the reality with the distribution of the stone columns or the rigid inclusion in the soil. So you do see that this is usually being characterized by a spacing in both directions, AB, which define an influence zone area, A times B. And the idea is to define the reference solution by first doing an equivalent axis symmetrical model, well, for those who do not have 3D. And you are defining the reinforcement in an axis symmetrical model, the dimension of which is set up such that the radius provides the same influence zone area as in the 3D reality. So in that case, if you work out the math, you can find out that the equivalent radius should be equal to square root of a times b over pi. And this way you are sure that in both 3D and axis symmetrical model, the size of the top surface is the same. That's what it is. So you are this way considering properly what we are calling the cyclic symmetry, and due to the fact that in fact you are not dealing with one stone columns or rigid inclusion, but an infinite group of them, and you're just focusing on one of them. Okay, so that defines the reference solution. So depending on the pattern you are considering, you see how the equivalent diameter or radius could be defined. Well, this is just doing some trigonometry. I don't think there is much interest to go into the details of those formulas here. And then try to more focus on this calibration process. Here on the left-hand side, we are doing the plane strain model. So this corresponds to how the columns would be represented in 2D situation. Yeah? And we are trying to match the results of this plane strain model with the one obtained from the reference axis symmetrical model that we have been defining before. Okay, and that's again, that's the calibration process, and the calibration process could be a bit different whether you are using a stone column or rigid inclusion. So if you are using, for instance, here, I guess it's a stone column. I mean, we are here looking into, for instance, the displacement profile at different locations, for instance, first in the axis symmetrical model and then in the plane strain model, and make sure that we do get proper match. And if we do not, so usually what I am doing to define in the framework here of the stone columns, I am just starting by having the equivalent thickness, which is the thickness for which I would obtain at the top the same contact area between the stone column and I would say the mattress on top of it, to the one in reality. So I'm making this equivalence, and this will define the equivalent thickness. And this way, I'm sure that although a 1 meter slice model, I have the same area in contact between my stone columns and the top mattress. Usually, when you start this way, you are not that far off. You are already quite close. And then if you really want to do like perfect fine tuning, you could start playing a little bit with this thickness in order to get perfect matching. And the matching has to be done on displacement profile as well as on the excess pore water pressure evolution of the degree of consolidation. Okay, so this is usually the way I do it for stone columns. For rigid inclusion, this is also something that we are doing. The calibration process might be a bit more elaborated because we also want to make sure that we are obtaining within the rigid inclusion also the same force, axial force distribution. So this is also takes some calibration techniques, especially on the embedded beam element parameters. I have decided not to present them today because I was a bit afraid to run out of time. But again, if you check out all the articles that Sequent has published, those techniques in both cases, stone column and rigid inclusion, are perfectly explained and documented, and as well as we are providing all relevant PLAXIS model for each situation. So feel free to reach out to us in case you would be interested to apply such techniques for your modeling needs. And then finally, I'd like to say a few words also to introduce the second case study of Jérôme, that will be talking a little bit about PLAXIS 3D. Also, do not forget that PLAXIS 3D also provides some added value in the framework of analyzing soil improvement. And main of them is that usually when you start doing 3D, although it could appear to be a bit more costly to set up the model, well, no calibration is required because 3D will do the most accurate representation of the reality and the soil structure interaction modeling. So usually the model are set up just considering one slice with one row of columns, and then that's the only thing you need to do. And then there is no calibration regarding permeability, regarding property of the structural element. And usually in that framework, if you are using rigid inclusion, they will be modeled as volume element, then introducing physically the diameter or the cross section of the rigid inclusion. And finally, the evaluation of the structural forces within such volume elements are done by the common techniques of the Doomy beams that consist of introducing along the neutral axis of each rigid inclusion a beam of low stiffness values in order to, in the post-processing environment, be able to access the structural forces, axial forces, and bending moment. So yeah, this is all for me. I will now give the floor to Jérôme that will now elaborate on more practical considerations on using PLAXIS for such type of soil improvement project. The floor is yours, Jérôme. Unless Daniel, you wanted to say something?
No, thank you a lot for the presentation. Jérôme, the stage is yours now.
I need to give the...
No,
okay.
all is ready. Don't worry.
Okay. So you should see my screen now, I guess. So thank you, Richard. Thank you, Daniel, for inviting me to this webinar. So I will be now sharing two different case studies. So I would like to start by the modeling of prefabricated vertical drains associated to preloading. So the project I will speak about is still ongoing and is based in Guyana, close to the capital city of Georgetown in South America. And it's a project about the construction of gas power plant, so 300 megawatt. So this is a picture of this 300 megawatt gas power plant. It is located here at 20 kilometers from the Atlantic Ocean, close to this river, which is the Demara River. And so the gas is coming from the Atlantic Ocean to this facility through a 20 kilometer long pipeline. And so the purpose of this facility is to generate electricity from the gas for domestic use. And the government says that the gas to energy project will cut the electricity cost of power by 50%. So a reduction of the cost of electricity by 50%, and also a reduction of CO2 emission because they can replace heavy fuel oil by gas. So let's focus on this power plant. So this is the layout. So a few information regarding the technical specification. So the existing ground level is at plus 1.5, corresponding more or less to the groundwater table. And the final grade level is at plus 3.5, meaning that you have a raising fill of 2 meters. And the post-construction settlement, so the residual settlement after 20 years shall not exceed 50 millimeter to 100 millimeter, depending on the areas. That's the technical specification, and that's why we need to implement ground improvement for this project. All the structure that you can see here, they will be then built over piles. So the purpose of this specification, is only to limit the impact of the raising field onto the piles. So to limit the negative skin friction onto the piles. So this is the general layout of the power plant, plus also the layout of the soil investigation campaign. So you can see a lot of cone penetration tests and a lot of standard penetration tests. So a lot of in situ tests, plus of course some lab tests. So let's have a look at this cross section to show you an overview of the soil profile. So this is the existing ground level at plus 1.5. Then you have the Demarara clay layer, so which is a soft clay layer. So you can see the tip resistance. This is a CPT here, so we have a very low tip resistance, a high water content between 60 to 100%, a high void ratio 1.8. So very soft clay layer, and below, still a clay layer, the Coropina clay layer, but which exhibit better soil characteristics. So I would like to focus on this area where the thickness of the subsoil is the highest one. So we can see the base of the Demarara clay layer is at -21. So the ground improvement solution consists of prefabricated vertical drains plus preloading. So let's have a look at the project. This is the initial level. We want to reach plus 3.5. So we want to add 2 meters of fill. The soil is soft. So if you install this fill, it will create settlement. So you need to compensate this settlement. That's why the preloading solution, you need to consider this preloading, this settlement compensation fill, plus, of course, the 2 meters of fill. The soft clay layer is fine and saturated. And so this settlement will be very slow if you don't do anything. So that's why we add some prefabricated vertical drain in order to accelerate the dissipation of excess water pressure and in order to accelerate the settlement. But despite the use of PVDs, we won't reach 100% of consolidation. That's why we also need to consider a surcharge in order to accelerate the consolidation again and to anticipate potential creep settlement coming from this soft clay layer. So the purpose of our design is to define the spacing of the PVDs and the total height of preloading required to ensure this residual settlement of 100 millimeters at 20 years. So this is the idea, to force settlement during the works and then at the end to remove surcharge and to guarantee maximum 100 millimeters. So a few words about vertical drains. Prefabricated vertical drains can be flat, as you can see here. They can be round. They are made of flexible polyethylene core, so surrounding by a geotextile. And these PVDs, they are installed by pushing a casing, as you can see here, within the drain. And once the required depth has been reached, the mandrel is extracted in the ground. And then at the end, you can see the PVDs is cut, let's say 20 centimeters above the working platform. It was already discussed by Richard. On site, we will have a square grid, a regular square grid of prefabricated vertical drains. We will be using PLAXIS 2D, and so we will have like a drain trench. So there are several approaches to calibrate the model. So you can play with the spacing, you can play with the horizontal permeability. So what we did for this project is we calibrate our model on an analytical result. So we run 2 unit cell calculation. On the left, it's without any PVD. On the right, it's considering the PVD. Okay, and you can see the soft clay layer. And the analytical solution has been obtained by the Barron theory. So based on the CV and on the CH, we were able to plot in red the degree of consolidation with time following this analytical approach. And then from the CV, so coming from the odometer test, we have estimated the KV for the PLAXIS 2D as a direct input of PLAXIS 2D. We have also estimated the KH, so the horizontal permeability. And what you can see on this model here is that with a spacing of 0.9 meter between the drain in PLAXIS, we were able to get a perfect match with the Barron theory. And globally, to give you order of magnitude, after 50 days, we have a degree of consolidation with the PVD around 80%. So once the calibration on the analytical results made, we can go to the global 2D plane strain model. So this is the initial condition. So we've run a consolidation analysis with activation of updated mesh and updated water pressure. So you can see the two clay layers, the Demarara clay layer and then the Corupina one. First step, maybe before, the soft clay layers has been represented by soft soil creep model. So you can see the different parameters, CC, CS, ENOD, all these parameters coming from the odometer test, and KX and KY coming, from CV and CH. The next step is the activation of the PVDs. And the preloading, the total preloading 8 cannot be installed in one step due to stability issue. So you will see that we've installed this preloading 8 in 2 steps. So first step, we add 3.9 meters of fill in 16 days. You can see that we have added a geogrid 600 kilonewton per meter. We have then a consolidation period of 28 days to allow for dissipation of the excess pore water pressure and also to get an increase of the shear resistance of the soil. An increase enough to install the second step. So in the second step, we have added 2.25 meters of fill. So at total, we have 6.15 meters of fill. So this second step has been reached in 20 days. We have then a consolidation period of 56 days. And at the end of this step, we have removed the surcharge to reach the final level at plus 3.5. Then we have reset all the displacement to 0, and we have run the calculation during 20 years to look at the displacement 20 years later. We have included also 2 safety analyses. So one immediately after the installation of the first step, and another one immediately after the installation of the second step of fill. Before going into details in the results, I would like to speak very quickly about consistency check. When we install embankment over very soft soil, there is a risk of slope failure. And the very important parameter is the end-range shear strength, SU. You can see that in red, this is the SU profile estimated at the beginning of the project from CPT and from vane shear test. But SU is not a direct input of the PLAXIS model. In end-range A, you need to give the effective shear strength parameters. So it's important for me to track the evolution of the shear stress to max with time to make sure that we don't overestimate the shear resistance. So here at the initial phase, we can see in green that we have a shear strength which is very close to our SU profile. And at the end of phase 1, after consolidation under the first step of fill, we can see that we have an increase of the shear stress in the range of 11 kPa, which was in the order of magnitude of the value which was expected. So important to follow this SU profile. Now let's have a look at the vertical displacement. So you have in black, this is the black curve is the evolution of the fill installation. So you can see the first phase with 3.9 meter fill and the second one to reach 6.15 meter of fill. And then after 120 days, we have removed the surcharge to reach plus 3.5. So the settlement, which we have recorded, is in the range of 2.2 meters. So the settlement must be read on the right axis. So after the second step, we've reached 2.2 meter of settlement. And then, of course, we had to check that after 20 years, we don't exceed 100 millimeter. So here we have only the result after 1 year, but I can ensure you that at 20 years, the settlement, mainly due to creep settlement, is 75 millimeters, so lower than the technical specification of the client. So to summarize, we have installed 6.15 meter of fill, and we've had 2.2 meter of settlement, okay? And at the end, we have removed the surcharge here, 1.95 meter of surcharge. That's the sequence of works which was designed for this project. And just for your information, without considering updated mesh and updated water pressure, we would have more settlement. So it's important here to take into account this option to have a better evaluation of the settlement. If we look at the horizontal displacement, after 120 days, we had in the range of 50 centimeters of lateral displacement. Now about stability, slope stability analysis, it's quite interesting to note that without GeoGrid, we would have had a factor of safety of 1.15, which is quite far from the allowable value of 1.50. Okay, and with the GeoGrid, 600 kilonewton per linear meter, we were able to reach 1.5, as you can see on the left side of this slide. And immediately after installation of the second step, this is the same results. Without GeoGrid, it would have been it wouldn't have been in-house. With GeoGrid, we have a factor of safety which is allowable. Let's move to the job site. So you can see a picture here of the project. So you can see 4 PVD rigs working together. You can see also the installation here of the geotextiles. So at total, you can see the grid. It was between 0.9 and 1 meter. We had up to 5 rigs, and we were able to do 500 PVDs per shift, so in 10 hours. So per shift, one rig can achieve 11,500 millimeter linear meter. Sorry. On this picture, you can see here the installation of the preloading field with different settlement plate, with piezometer, with inclinometers for monitoring of the results. So this is the layout of the different monitoring sensors. I will focus at this location here, where we have a settlement plate and where we have an inclinometer. So on the left, you can have a look at the vertical displacement. So this is the vertical displacement with time. So it was this year, you can see. According to the installation of the field, you can see the first step and the second step. What we noticed is that the settlement was a bit slower than expected. So we had to add, one more surcharge, one another step to make sure. So what we did, is that we had a behavior which was a bit slower than expected. So we calibrated our PLAXIS 2D model, and we had to, to fine-tune a bit our design during the construction. But at total, you can see the total settlement is in the range of 2 meters at the end, so very similar to the initial prediction. And regarding the horizontal displacement, so coming from the inclinometers, we have in between 40 to 50 centimeters of horizontal displacement. So the initial prediction were quite in line with reality. So that was a good project at the end. Before maybe going to the next presentation, do we have some questions, Daniel, on this first case?
Yeah, we have actually a lot of questions. I will try to pick one now so that we can get other later. What are the benefits of the updated mesh and updated water pressure options?
Yes. Okay. Good questions. Thank you, Daniel. Actually, you can see that the settlement was quite high, 2.2 meter of settlement. That's why it's important here to select updated mesh in order to take into account large deformation analysis first. And then why updated water pressure? It's because you can see you have one part of the field which is going underwater. So in order to take into account, to consider the pore water pressure at the correct location, you need to use this updated water pressure option. So, and it's, yes, important because you have large deformation and one part of the field going below the water level. So let's go to the second case study. Thank you, Daniel, which is about footing over soil reinforced by rigid inclusions without any load transfer platform. I will explain a bit later, and subjected to an incline loading. So, I mean, we will have vertical loading plus horizontal loading. And to analyze this behavior, we did at the same time a zone load test on the site and PLAXIS 3D modeling. So this is the layout of the test we did. So you can see the footing here, 2 by 2, with 4 rigid inclusion in green. You can see the 4 rigid inclusions, 320 millimeter diameter, and you can see the pouring of the foundation concrete here. Then, in order to apply a vertical loading, we've used a plate plus a jack and of course a reaction system. And the reaction system is made of this beam plus 4 piles on each side. So you can see in red the 4 piles, the 4 reaction piles on each side. So this is to apply a vertical loading on top of the footing. And then we have also installed 2 piles here in red plus a concrete block which is a reaction system in order to apply an horizontal loading. So you can see here on this picture, the plate, the jack, and the reaction system in order to apply an horizontal loading onto the footing. We had a lot of sensors to monitor displacement, pore water pressure, vertical stress. We had also we also built a footing over non-reinforced soil, to have a reference results. So I will focus only on the results coming from the footing over the 4 rigid inclusion. So this is the different calculation we've done. The vertical load is always 100 tons, okay? But we have increased the eccentricity of the vertical load. In the first calculation, the vertical load is at the center of the footing. Then we have an eccentricity of 30 centimeter, 45 centimeter, and finally 67 centimeter. And for each calculation, we also apply an horizontal load of 20 tons. So it means that the inclination is, let's say, 20%. I mean, the ratio horizontal over vertical is 20%. A few words about the soil conditions. So the soil conditions were really easy. 1 meter of fill, 4 meters of loose silt, and then very dense sand and gravels. So why did we analyze the behavior of a footing directly on top of the rigid inclusion? It's because it's a very common situation for industrial building, for warehouses. So the slab is supported by soil reinforced by rigid inclusion, and it is associated with a load transfer platform. But the footing that supports the column, they rest directly on the rigid inclusions. okay, without any load transfer platform. And so the purpose of this research was to evaluate the behavior of such footing for a situation where the inclination is 20%. And here on the left, it's an extract from the new Eurocode 7. So it will be published in 2027. But it's an extract from chapter 12 about ground improvement. And you can see that we are in situation number C. Okay, this situation is clearly considered by the new Eurocode. We have a straight foundation without a load transfer platform. And the difference between piles is that we don't have any structural connection between the rigid inclusion and the structural foundation. That's the difference between rigid inclusions and piles. There's no structural connection. So please have a look at the 3D model that we have performed. So you can see the footing on the top with a vertical load only here, which is with an eccentricity. You have the difference, you have the fill, and you have the loose silt in yellow. So I will remove here the footing so that you can see the two rigid inclusion. By symmetry, we were able to represent only half of the model. So if I remove here the loose silt, you can see the rigid inclusion, the volume element with the interface. So you have interface around the rigid inclusion and below also the footing. And if you can see, we have also a dummy beam here in pink that was presented before by Richard. So this is the 3D model that we have run. So some pictures, some results. Result with considering the vertical load only, we were able to look at the vertical displacement, at the horizontal displacement, and also at the compressive stresses inside the CMC. Of course, if you have an eccentricity, as it is the case here, you will get more axial load in this CMC rather than in the other one, which is here. So this is with vertical load only. If you add an horizontal load, so here we are adding an horizontal load of 20 tons. So we can look at the vertical displacement, horizontal displacement. And what is interesting here is the behavior of the rigid inclusion. You can see that this rigid inclusion is subjected to bending moment. You can clearly see that you have bending moment at the top of this rigid inclusion. And that was the purpose of this research, to understand the behavior of rigid inclusion without any LTP. So I would like to finish with some results. So I would like to show you some results of this calculation. So you will see here the horizontal displacement of the rigid inclusion, the horizontal displacement of the soil, axial force in the CMC, bending moment in the CMC, and extreme fiber stresses in the CMC. Let's start with a vertical loading at the center of the footing. You can see the horizontal displacement of the CMC, of the rigid inclusion, which are exactly the same of the horizontal displacement of the soil. So we have 7 millimeters of horizontal displacement. The axial force are the same ones, or more or less the same ones for each CMC. The bending moment is very limited. Now, let's move a bit the vertical load. So I have shifted the load of 30 centimeters. So let's have a look at the results now. The horizontal displacement are more or less not really affected. But if you look at the axial force of the CMC, of the rigid inclusion, you can see that this CMC here, which is located directly below or below the vertical load, is subjected to 300 kilonewton of axial force, as opposed to this one, which is subjected only to 100 kilonewton, because it is located here, quite far from the axial, from the vertical load. And the bending moment is a bit higher than previously. And finally, considering the highest eccentricity, let's have a look at the results. Here we have very significant differences. If you look at the horizontal displacement, you can see that you have one CMC directly below the vertical load, which is moving a lot, 15 millimeters, exactly as the soil is moving. the CMC at the rear here, at the opposite direction of the eccentricity, does not move at all, almost nothing. And if you look at the axial force, you have a maximum axial force here in this CMC, and you have almost zero in this rigid inclusion. So if you look at this rigid inclusion, you can see that the axial force is close to zero. Looking at the bending moment, this CMC is subjected to high bending moment, around 20 kilonewton meter, whereas the other CMC does not see anything. The bending moment is almost zero. So from this research, we were able to define this conclusion. If the inclination is lower than 20%, there's no need to reinforce rigid inclusion. And we have more or less generalize this idea. And if the inclination is higher than 20%, you must run a calculation. Attention should be paid. Either you add a LTP, a load transfer platform, or you can also reinforce the CMC. But you have to be careful when you have high horizontal loading. Yes, I'm more or less on time. Do we have some questions, Daniel?
Yeah, we have a lot. Let me pick one. Jerome, first of all, thanks a lot for the case studies also. We should mention this. The question is, there is no load platform in your rigid inclusion modeling. What would be the impact of having a load transfer platform?
Yes, okay, so there's no LTP, as you can see here. We have directly the footing on top of the rigid inclusion. So if we had a load transfer platform in between the rigid inclusion and the footing, it will necessarily increase the vertical displacement of the footing, because you will get some actual load. You will get some part of the load going through the soil. So if you add an LTP, you increase the settlement. But at the same time, you will also reduce the bending moment. So it's a compromise. It depends on project. But I would say if you add an LTP, you have an advantage. You will reduce the bending moment, but you will also have a drawback. You will increase the settlement. So it's really depending on project. For project where the load is mainly vertical, no need for an LTP. If you are in seismic areas, for instance, where you have huge horizontal loading, it's better to have a load transfer platform to limit, the bending moment inside the rigid inclusion. So that's the main aspect, I would say.
Thank you a lot, Jerome. Thank you a lot for the presentation. To learn or try what you saw today, and especially also the soil improvement practical example, don't forget to request the PLAXIS trial. Also, that will be available on the campaign page. In addition, as we care about the feedback, you will receive in some time an email with the feedback. So we are waiting for your ideas for future webinars. Thank you all. Thank you, Richard. Thank you, Jerome. Have a nice day. See you soon in future webinars.
Bye.
Bye. Thank you.
Bye.